Hello Calc 3, welcome back to another video. So in this video we will cover the first half of section 16.3 on path independence of line integrals and conservative fields. So remember from a previous video, I think the first half of section 16.2, I mentioned that a line integral from point A to point B often depends on the path that we choose to take from point A to point B. However, in some instances, the value of the line integral does not change regardless of the path taken from A to B. And in this video, we will discuss the special circumstances when a line integral is independent of path, hence the topic path independence. Okay, so here's our definition of path independence as well as the definition for a conservative vector field. So if we let F be some vector field defined on an open region D in space, and suppose that for any 2 points A and B in D, the line integral of F over the curve C that connects the points A and B in D is the same over all paths from A to B. So if this is the case for any 2 points inside of the open region D in space, then we say that the vector field F is conservative. So if, regardless of the path that we take from A to B, the line integral of F over that path is the same, then we say that the vector field over that region D is conservative. And for the particular integral that goes from the point A to the point B, so if we're talking about particular points now, if that integral is independent of path, then we say that the integral is path independent. So another way to view this is a vector field such that the integral from any 2 points inside of the region D is path independent. That field is going to be a conservative field. That's another way to look at it. Okay, so if a line integral is path independent, we will often write the line integral of F over C as the integral from point A to point B of F. And this is because regardless of which path we choose to connect the points A and B, the integral is going to be the same. So in this case, it's not ambiguous for us to just write that the integral goes from the point A to the point B in space. So ultimately, we end up finding that a vector field F will be conservative if and only if it is the gradient field of some function f, so that the vector field F is equal to the gradient of the scalar function f. And this leads us to our next definition. So if the vector field F is defined on a region D, and the vector field F is equal to the gradient of little f for some scalar function little f, then little f is called a potential function for big F, for our vector field. And if we can identify a potential function, little f, for our vector field F, then evaluating line integrals of our vector field F becomes relatively simple. As we will see shortly, in particular in the rest of the video, this is what we're going to be looking at. And ultimately, for conservative fields, there is a theorem analogous to the fundamental theorem of calculus, allowing us to evaluate line integrals. So remember that the fundamental theorem of calculus, or I think part 1 of the fundamental theorem of calculus from Calc 1, was that if we have a definite integral from a to b of some function f of x dx, then we can evaluate that definite integral by finding antiderivatives of f. So we can find an antiderivative of f, call it big F, and that integral is going to equal big F of b minus big F of a. So I think this is part 1 of the fundamental theorem of calculus. Maybe it's part 2. I don't remember. But regardless, it's the fundamental theorem of calculus from Calc 1, and we have an analogous theorem that's going to pop out soon enough for line integrals. So before we begin that discussion, there are some assumptions that we have to talk about first because they're going to be relevant to the preceding theorems. for the rest of the video. So for the preceding discussion to be true, we need to assume some things about the vector field F and the region D on which F is defined. So first off, all of the curves that we talk about or that we consider within the region D are piecewise smooth curves, meaning that they can be constructed by attaching smooth curves end to end. So we can think about all of these curves as looking something like this. We have a smooth curve that goes from here to here, and then we can attach another smooth curve that maybe goes from here to here, and then we could attach another smooth curve. And all of these curves, when we take the union of them together, are going to create one curve, which will be piecewise smooth. So that big curve is created of smaller curves that are smooth. Also, all of the vector fields will have component functions with continuous first partial derivatives. So remember that the vector fields can be written as something like this. So we have F is equal to m times I plus n times j plus p times k, where big M, n, and p here are the component functions, usually in 3 variables for F here. And we're assuming in all of the preceding discussion that these component functions will have continuous first partial derivatives. So that is important. Next up, all of the domains D that we consider will be connected. So I've drawn little diagrams on the right here to talk about what connected means. I guess a nice intuitive way to think about it without getting into topology is that connected basically just means that we don't have a separation of regions inside of the domain. So if you look at the example that I have on the right here, notice that I can't travel from this point to this point without leaving the one region or the domain here. So if I wanted to try and travel from this point to this point, I'd have to go outside of the region to get there. Whereas if I pick any 2 points inside of this region over here, there's always going to be a path inside of that region that allows me to get from one point to the other point. More specifically, this is called being path connected. But again, that's more so in the realm of topology. We don't have to worry about that here. Hopefully these pictures give you an idea of what we're talking about here. And secondly, some of the domains D will also require D to be what's called simply connected. And for a region to be simply connected, it means that every loop in the region D can be contracted or shrunk down to a point without leaving the region D. And a more intuitive way to think about this is you can think of it as domains that don't have any holes. So if you look at the example I have up here, this is an example of a simply connected domain. If I pick any loop inside of that domain, notice that I can shrink it down, contract it down on itself, and as I do that, it's still going to remain inside of the region, and I can contract it all the way down to a point. However, if you look at the domain that I have below there, this domain has a hole inside of it. And if you draw a loop around that hole and then you try to contract this purple loop that I have here down to a point, at some point you're going to leave the domain. So you're going to exit the domain. And for that reason, you can't contract this loop down to a point inside of the region, and therefore this region here would not be simply connected. So that's something to keep in mind as well. The necessity of a domain being simply connected will show up in one of the theorems later on in the video. So just keep that definition in mind. Okay, so now that we've gotten the preconditions out of the way, we can move on to talking about line integrals in these conservative fields and hopefully deriving some properties of these kind of line integrals. So here's the first theorem, probably the most important theorem of the whole section here. It's called the fundamental theorem of line integrals, so I'll refer to it as that later on in this video and the next video. So let C be a smooth curve that joins 2 points A and B in the plane or in space, and let C be parametrized by some vector valued function r of t. And let little f be a differentiable function with a continuous gradient vector, big F equal to the gradient of f, on a domain D that contains the curve C. So we have some domain, maybe it looks like this, and then we have our curve that's running through the domain that might look like this. And again, this red region is going to be the domain of big F, which is a vector field, and we have a curve that's parametrized running through it. We can call this point A, and we can call this point B. So if this is the case, if all of these preconditions are met, then the integral of the vector field f over the curve C is equal to little f at B minus little f evaluated at A. So this is the analogous theorem to the fundamental theorem of calculus from Calc 1. And like the fundamental theorem of calculus, this allows us to calculate line integrals by finding a potential function f, little f, and evaluating at the endpoints of the curve. Okay, so let's move on to an example where we apply this fundamental theorem of line integrals. So suppose that the vector field f is equal to the gradient of little f, where little f of xyz is equal to -1 over x squared plus y squared plus z squared. Notice that the denominator of that function for little f there is the square of the distance of a point from the origin. And we want to find the work done by the vector field f in moving an object along a smooth curve C that joins the points 1, 0, 0 and 0, 0, 2 that does not pass through the origin. So the importance of the fact that this curve doesn't pass through the origin is that if the curve passed through the origin, we would be leaving the region on which little f is continuous. So notice that little f is not defined at the origin because we would get 0 in the denominator. So we need to make sure that whatever curve we choose doesn't pass through the origin in order to use our fundamental theorem of line integrals here, because again, we assume in that theorem that f is has a continuous gradient vector. So we need f to be continuous. And we are going to use the above theorem. So we know from section 16.2 that work is equal to the integral of f over the curve C. And the theorem above tells us that that is equal to little f evaluated at 0, 0, 2 minus little f evaluated at 0, 0, 1, because f is the potential function for the vector field f. And this ultimately gives us -1/4 minus -1. So we just plug those 2 points 0, 0, 2 and 0, 0, 1 up into our function for f. And evaluating will give us 3/4. So the work done by the force field F in moving an object along that curve C is equal to 3/4. And here's an interesting note to keep in mind. The gravitational force due to a planet, as well as the electric force associated with a charged particle, both of these concepts can be modeled by this vector field in the previous example that we just went through, up to a constant that depends on units of measurement. So this little f ends up being a potential function for the vector fields that describe gravitational and electric force. And consequently, or maybe not consequently, but regardless, gravitational and electric forces and electric force fields are conservative fields. And the proof of this fundamental theorem of line integrals is given in the textbook. I am not going to go through it here. So next up, for the next big theorem of the section, we have the theorem stating that conservative fields are gradient fields, and this is actually an if and only if statement. So if we let f equal mi plus nj plus pk be some vector field whose components are continuous, throughout an open connected region D in space, then f is conservative if and only if, meaning that this goes both directions, f is a gradient field for a differentiable function f. So this means that our vector field is equal to the gradient of little f, where f is some differentiable scalar function. So this is another pretty powerful theorem. So f is going to be independent of path, or the line integrals of f will be independent of path if and only if we can write f as the gradient of some differentiable function f. So if big F is conservative, then we can find a potential function little f for big F. And the fundamental theorem of line integrals, the theorem that we just covered previous to this up here, the fundamental theorem of line integrals gives us that the gradient field implies conservative field. So if we have a vector field that can be written as the gradient of some differentiable function, it follows that that field is going to be conservative. And again, the proof of this theorem is in the textbook. You can email me if you're interested in the proofs of any of the theorems that are in here and you're having trouble understanding them. I just don't want to cover them in the video because the video would be probably needlessly long. So in order to cut down on some time, we're going to keep some of those proofs in the textbook. Okay, so let's move on to another example then. Let's say we want to find the work done by the conservative field f equals yzi plus xzj plus xyk, which is equal to the gradient of f, where f of xyz is equal to xyz. So you can check if you want to that this vector field here is in fact the gradient of this function f of xyz. And we want to find the work done along any smooth curve C that joins the point -139 to 16, -4. Okay, so since f is conservative and f is a differentiable function with a continuous gradient vector, we have that the line integral of f over the curve C is equal to the integral from a to b of the gradient of f dot dr. So here we can write a to b as the limits of integration because of path independence, and then we just substitute the gradient of little f in for big F because we know that big F is equal to the gradient of little f. And from there, the fundamental theorem of line integrals tells us that this integral from a to b of the gradient of f is equal to f evaluated at the point B minus f evaluated at the point A. And so we can take these points and plug them in for little f. So we get xyz evaluated at 16, -4 minus xyz evaluated at -139. And ultimately, after doing some calculation here, we end up finding that the answer is 3. So in this case, the work done by our conservative field f along any smooth curve that joins these 2 points A and B is going to be equal to 3. Now finally, we can move on to the last theorem for this first video for section 16.3. This theorem is entitled the loop property of conservative fields, and it goes as follows. So the following statements are equivalent. The first statement is that the integral around a closed curve C of f is equal to 0 around every loop in D. So that's the first statement. And the second statement is that the field f is conservative on D. And this theorem is saying that these statements are equivalent to one another. What does that mean? It means that if 2 is true, then 1 has to also be true. And if 1 is true, then 2 is also true. So if it's the case that inside of a region D, the integral over any closed loop inside of that region, maybe I should even draw a little picture. So let's say that our region D looks like this, and we can pick any loop inside of here. And if we integrate around that loop, the value is going to be 0. So any loop that I choose inside of here, maybe it looks like this, maybe it's really small like this. Regardless of which one we choose, statement 1 is saying that the integral will always be 0. And statement 2 is saying that our field f will be conservative. And these statements are equivalent to one another. And for this theorem, I will give a proof because I think that it's instructive and relatively visual. So hopefully you can follow along here. So first, we're going to prove that if statement 1 is true, then statement 2 is also true. And after we prove that, then we'll move on to the proof of the reverse direction, that if statement 2 is true, then statement 1 is also true. Okay, so starting off with the proof that 1 implies 2. So assume that statement 1 is true, meaning that if I take the integral of f over any closed curve, C, the value is going to be equal to 0. And now let A and B be arbitrary points in the region D, and let C1 and C2 be smooth curves that connect A and B. So I've drawn these 2 points inside of the region D, and we have 2 curves that are connecting A to B. And to show that f is a conservative field, I need to show that the integral of f over curve 1 is equal to the integral of f over curve 2. And if I can do that, I can conclude that f is conservative because the points A and B are arbitrary and the curves, curve 1 and curve 2, going from A to B are also arbitrary. So if we pick these 2 curves, C sub 1 and C sub 2, going from A to B, then we can reverse the direction of C sub 2 and call this curve negative C sub 2. So notice that in this case, the arrow is pointing in the opposite direction. Negative C sub 2 goes from B to A. And if we combine C sub 1 and negative C sub 2, then notice that we get a loop that starts at A and ends at A. And by assumption, the integral over this loop, which is C sub 1 union with minus C sub 2 of our vector field f, has to equal 0, because that has to be true by statement 1. The integral is equal to 0 around every loop in D. But we also know from section 16.2 that this integral of f over C sub 1 union minus C sub 2 can be written as the integral of f over C sub 1 minus the integral of f over C sub 2. So this is the additivity of the line integral here. So we can rewrite it that way. And again, we know that this has to equal 0, but now we can add the integral of f over C sub 2 to both sides of this equation here, and we end up with the integral of f over C sub 1 is equal to the integral of f over C sub 2. So the line integral from A to B is path independent because C sub 1 and C sub 2 are just arbitrary paths that we chose from A to B. And since A and B are arbitrary, we can conclude that f is conservative. So that gives us the first direction. If statement 1 is true, then statement 2 must also be true. And now we want to move on to the reverse direction, proving that if statement 2 is true, then statement 1 must also be true. So assume that statement 2 is true, meaning that f is conservative on some region D. And let C be a closed curve in this region D. Then we can pick 2 points, A and B, along this closed loop that we now have inside of our region. So this red loop here is going to be C, and I've picked 2 points on the loop A and B in purple. Then C, this curve in red, is a piecewise smooth curve consisting of C1, which is a curve from A to B, so maybe I should write that as well. So let's call this C1 going from A to B, and then we have a second curve going from B to A, which we will call C2. So the integral over this closed loop C is equal to the integral of f over C sub 1 plus the integral of f over C sub 2. And again, this is just the additivity of the line integral. Maybe I should write that. So additivity of line integral from section 16.2. But because the vector field f is conservative, we can just write this, this integral of f over c sub 1 as the integral from a to b, because we have path independence. And the integral of f over c sub 2 we can write as the integral from b to a, again because we have path independence for both c sub 1 and c sub 2 here, because f is conservative. But this integral from b to a of f is equal to negative the integral from a to b of f. And now we have the integral of f from a to b minus the integral of f from a to b, which is of course equal to 0. And so in this case, we picked some arbitrary loop inside of the domain D, and we've showed that the integral of f over that loop has to equal 0. And because this loop is arbitrary, the line integral of f over any closed loop in D has to equal 0. And so for that reason, statement 2 implies statement 1. And that is the end of the material for the first half of section 16.3. The second half of section 16.3 should be showing up on YouTube sometime relatively soon, so look out for that.